Welcome once again to Natural Habitat Adventures' daily dose of nature, migratory species, not all who wander are lost, with expedition leader Kristina Disney. Kristina, thank you so much for being here today. We appreciate it. I'll turn it over to you.
Thank you so much, Colby. It was lovely to get to see you. I haven't seen Colby since polar bear season 2019, so it's nice to catch up with a friend. Hi, everyone. My name is Kristina Disney, and as Colby said, I've been an expedition leader and guide with Natural Habitat for a couple of years now. Normally we do a little bit of an intro about ourselves, but I thought, given the theme of our presentation today, that I would actually share with you all my favorite poem, so much so that it's actually the only poem I have memorized the whole way through. It's called Wanderlust, fitting with our theme. So it's by, I think, J.L. Gould. Beyond the east the sunrise, beyond the west the sea, and east and west the wanderlust that will not let me be. It works in me like magic, dear, to bid me say goodbye, for the seas call and the stars call, and oh, the call of the sky. I know not where white road runs, nor what blue hills are, but man can have for his friend, the sun for friend, and for his guide a star. And there'll be no end of voyaging when once the voice is heard, for the river calls, and the road calls, and oh, the call of the bird. And yonder beyond horizon lie, and there by night and day, the old ship sets home again, the young ship sails away. And come I may, and go I must, and if men should ask you why, you may put the blame on the stars, the sun, the white road, and the sky. So if you can guess from that, I like to move around a lot. It fits with our theme, and so I was very excited to get to have a whole topic about navigation and migration. And before we delve into our animal kingdom navigation, I thought we'd do a quick spin through some of human navigation through the years. And so different groups have been nomadic, crossing huge tracts of land throughout the years. And so none of that's new, you're losing landmarks, these cues, things like that. But really, we've pushed navigation when it comes to moving at sea. So thinking about ancient sailors, most of the time kept within sight of the coast because they couldn't trust that they would be able to make it home. We do know, obviously, people like Scandinavian Vikings crossed the open ocean. There was the Minoan sailors who lived in the Mediterranean around Crete, and there's evidence of them from about 3000 BC to 1100 BC using the stars to navigate. So there is evidence of ancient civilizations traveling further away from shore, but it was definitely out of the norm. And so what you and I know is the compass, one of our primary aids to navigation, even though we don't think about actively using it so much today, was actually invented around the 2nd century BC, 1 AD. It's one of those ones we're not quite too sure, but it was invented during the Han Dynasty in China. But it wasn't used for a navigational aid. It was actually almost more of a trinket or what they would use for predicting futures or things like that. And people didn't start using it as a navigation aid until around the 11th or 12th century. So thinking about that, one thing I think is really cool is that the translation of the earlier compasses wasn't the translation from Chinese we would translate into English as south pointing fish. And so early compasses were often a string with a magnetic load or a iron that had been magnetized, and then you would either wait for the string to spin or you would have it floating in a bowl of water and wait for that to turn, which I just thought was a very neat thing. And so our ability to navigate throughout the years has gotten better simultaneous to, or largely because of our ability to measure time. So I don't know if any of you out there do this, but someone will ask, how far away is something? And instead of answering them in miles or something like that, you're answering them in time. It's like, oh, it's a 2-hour drive. Oh, it'll take you 30 minutes to get there. And so our ability to travel and to navigate is intrinsically linked to time. And so as we got better at measuring more defined segments of time, hours, minutes, seconds, things like that, we also simultaneously got better at being able to navigate. So for example, sailors couldn't really track their longitude until they were able to keep track of time along the ship. And so through the years, our ability to, keep track of where we are to navigate while sailing has gotten progressively better. So moving on our images from left to right. So the first one you see there is called cross staff. That was in the 1300s, and it's that simple geometry that we learned, you know, Pythagorean theorem, trying to figure out angles and keeping track of the angle of the sun as far as you are. Then around the 1600s, we got the quadrats, and it's the same thing. You're figuring out angles of stars based on where you are. And then the 1700s, we got the sextant, and that was kind of the Cadillac of the medieval times of being able to keep track of where you were. I have a personal favorite of medieval navigation devices. This is called an astrolabe. I think about it as it's almost like the Leatherman or the Swiss Army knife of medieval navigation. So it's cool. It's a multitude of discs. And what you do is you turn the discs based on your zodiac date, and then you can line that up. And so after you align the discs, you can essentially use it to measure things like elevation, distance, tell time. They were super functional, which I think is, you know, I want to carry one of those around instead of a pocket watch. I think that would be cool. It's on my bucket list of life. But of course, today we have certainly advanced. We now have our global positioning system. We've got satellites. I know I'm guilty. My phone is just off screen here, carrying around woes in their pocket. So we don't often think about it, and of all of the steps that have gone into getting where we are. And I realize I've just taken us through about 1,000 years of navigational history, and some of you may be sitting there thinking, hang on, where are my feather furry friends? This isn't what I signed up for. And I promise I'm coming back to them. I just wanted us to take a trip down navigational memory lane, because while humans have spent the last couple thousand years really honing our skills, this exact same argument can be made for the animal kingdom. And I would say that they have certainly surpassed us in many regards. And so I wanted to start us off actually with a story from when I was younger. So what you're seeing here, this is the town, not that I grew up in, this is where I would have more or less grown up in southern Saskatchewan, and really small hidden place in the corner. And when I was, I don't know, grade 7, 8, somewhere when you're like 11 or 12, we did a trip to a national park nearby where I grew up. And this trip was really, it's interesting, I didn't really think about it until I was making this presentation for you all of how important this trip was to me developmentally, because it was the first time I met a parks biologist. It was the first time I realized that like conservation was a career I could explore. And so I thought, like, I've never forgot this trip. I remember everything he ever, like the parks met, I guess not the word, the biologist's name was Owen. And I like remembered everything that he said. And yeah, so there's this really fascinating story. Essentially what happened in Grasslands National Park was that they wanted to repopulate it with bison. So I've got a map here. This is showing you, the dotted line is the border between Alberta and Saskatchewan, just for a bit of reference. So those in the Canadian provinces, we're kind of in that grasslands open area. And so there's 2 parks. And so in the 80s and 90s, they rebuilt up the bison population, and Elk Island was the one that did that. And then they decided they wanted to populate this other national park as well. And so they hauled a truckload of, I think it was less than 50 bison originally. And the interesting thing is that they drove them down, right? So you're in one of those big cattle liners you may or may not have seen going down the freeway. And so they were drove from the one park to the other. So more than 800 kilometers, right? So you're at more than 500 miles, give or take a bit. And what's fascinating is that those bison that were hauled there, when they dropped them off, so you know, they go unload them, all the bison blitzed. They ran for the northwest corner of that park. And for years, the parks people tried to get them to go feed anywhere else. They tried to get them to go to the south side. They tried to get them to the west. They would like, and they would always, anytime, you know, if they went in and with horses and moved them south, then as soon as they were done moving them, they would turn tail and go back, because they kept trying to leave the park. They were trying to go back to where they had come from. Even though they had been drove in a truck, even though they never walked it themselves, and they probably couldn't see half the time on the way there, they knew where they came from and they tried to get back. And it took, I think the parks manager said, almost close to 5 to 7 years. It took a couple calves, like the bison calved a few times and settled in before they actually started to explore the rest of the park and not try to go back. So not only did they know where they came from, but they hung on to that for a very, very long time before they accepted it. And so now there's enough generations there, it's established, and they roam the whole park. But that question stuck with me for years. I was like, how in the world did they know where they had come from? And so that's what we're going to really try and dig into some of that today. So we're going to look at 4 different methods of navigation. We're going to look at how different animals use celestial objects, how they build mental maps, smells and pheromones, which is a personal favorite of mine, and magnetic fields. So I'm going to get again a little bit here. We'll try and break this up bit by bit. So when we think about animals using the sun to navigate, and we do too, right? You wake up in the morning, you look, oh yeah, there's the sun, you kind of know roughly what direction you're looking at, what time it is. But animals are far more in tune. But it's interesting to think, right? Because if the sun stayed in one spot, it would make sense that they could use that as an anchor point, and they're like, yep, sun's always there, but the sun is always moving. So what animals do in order to keep track, to use the sun to help them navigate, is they do 2 things. So the first thing they do is they sync up their internal clock, so their circadian rhythm when they wake up and go to sleep. They sync that up with the azimuth of the sun. So when I say azimuth, that's about the angle of the sun with from north. And when they get those synced together, then they can essentially, as the sun moves through, keep track of that direction relative to time. So let's take a step back and think about this. So you and I, we have a circadian rhythm too. Everyone's is a little bit different, but a really good example is, when you have a flight and you've got a red eye or something and it's 2 a.m. and you're so worried that you're gonna miss it, and you've set, 6 alarms, whatever it is, and you wake up before any alarm's gone off, and it's like 1 minute before your alarm would go off, right? Your body knows what time it is. It's keeping track. We maybe consciously don't, but our body is in tune with that. So animals use that very in tune clock inside themselves to pair up with the angle of the sun. Now, we all generally, right, sun rises in the east, sets in the west. That's what we always say. But really, we also know that that's not entirely perfect, right? So it's usually, in the wintertime, the sun is further south of us for those of us who are in the mid latitudes of Canada or the US. And then right, so that changes time of year and where you are in the world. And so, for us right now, the sun's a little bit to the south, and then it's going to come over and rise, and then it goes up. And so it's always on a bit of an angle. And so what animals do is they think, okay, here's north, and so they always measure the angle of how far is the sun from north, how far is the sun from north. And so their brains are always computing those 2 things and putting them together. And so that's what we call a time compensated compass. So they're using time to figure out direction, which I think is pretty amazing. One of the animals that does this is the honeybee. And I don't want to have time to go into, I could talk about honeybees for an hour exclusively. I love bees. I think they're so cool. So first of all, a waggle dance is what they use to help communicate the direction of where they find food sources. If you haven't heard of a waggle dance, when we're done here, definitely go look it up. It's really cool. Go watch some videos. It's very fun. But essentially, they dance information of where you need to travel to find the pollen source. And so they did a study on how bees use the sun. And so what they actually did was they took a hive, and there's a tree line and everything's there, and they moved the hive. And what they found was that the bees were still dancing the same directions as if they were at the first place. They were in tune to that location of where the sun was, and now that it was moved, their dance didn't make any sense. And so you can tell, it's one of the ways we figured out how they're using the sun to navigate. Another one that there's been a lot of cool research on is the starling. And actually, this was a while ago. Like, this work was done in the 50s. And what they did was they had all the starlings, and they took mirrors. So there's the sun coming down, and then they used mirrors to shift the direction of the sun by 90 degrees. And they found that when all the birds then interacted and were orientating themselves, the birds all shifted. So the birds thought that the sun was coming from, let's say they shifted at 90 degrees to the north. So then all the birds would fly that way, thinking that was actually east. So again, we're seeing how they're using that to travel. But then comes the question of, what about at night, right? What about when you don't have the sun? And one group of animals that's specific nocturnal migrators is songbirds. They primarily migrate at night. So this one here that we're looking at is a green warbler. And they did a really cool study on it when they were trying to figure out, so if they're navigating by night, we assume that they navigate by the stars. But how are they doing it? What are they honing in on? What sort of information are they looking for? And so what one researcher did was he had a bunch of warblers in a room, and each was in a corner. And then above each one, you know when they have those things for little babies and they've got the things hanging down and you can play with it? It was like he had a special star sky designed for each corner of the room with different dots in it, and then it would turn, so it would mimic our sky. But the way that he did was he had it focus on, one had what our sky looks like with the North Star at the center and everything spinning around it. But then he would pick different stars and spin around them. And then when he released the bird, they would all fly. They would all orientate themselves based on the stars that they had grown up under, which I think is really quite cool. And so from that, we learned that inherently, birds are using that poleward direction. So they know they're born with the ability to figure out what poleward is. So when I say that, they can figure out north-south. But then they train themselves to follow that circular pattern. And when we're looking at this I guess is just a fun fact, so that I like to share this. I'm a big star nerd as well, so that's a nice bonus. So wherever you live in the world, the distance from the horizon to the North Star is your latitude on Earth. So if you, right now I'm pretty much at 49 degrees latitude. So if I stand outside at night tonight and I look up and I measure the distance from where I'm standing to where the North Star is, that's gonna be 49 degrees. So that's a cool trick you can show someone you're out with the next night of figuring out when you've gone somewhere new in the world. Which is also why when you go to the equator, the North Star is directly on the horizon. If you're right on the equator, it should be just like right there, which is a cool thing. Yeah, so our green warbler buddies, they're born with that inherent ability to figure out polewards directions. And these are some of the things that we've learned about how they're navigating, but things that are still quite mystical, things that we still don't have explanations for is juvenile songbirds. The first time they navigate, especially when they navigate solo, we still don't really understand. There's still much that's happening in the genetic code where that information is being transferred that's not a learned behavior. So there's still a whole lot of stuff to learn, and it's just really cool how they're able to do that. Another way that they're able to navigate is by building mental maps. So this should be, this one is more intuitive for us to understand, right? Think about your high school, wherever that was, however long ago that was. Think about if you were to walk into your high school right now, could you remember where your locker was? Could you even remember where your high school combination was? Maybe you don't remember the numbers, but I find there's a certain amount of muscle memory in your hand, right? When you're figuring out the numbers, some part of you can still hang on to those things. And so exploratorily, mental maps, a lot of species, this is how they start mapping it out, right? They're very, very good at remembering. And so the further they explore, the greater they build their map. And there's a cool study done with mice that essentially showed that there doesn't have to be a reward to exploration. It doesn't as in, it's not as if the mice would only explore if they found a snack. They would keep exploring all the time. They're always covering as much ground as possible and always fleshing out that map. And I'm not sure if any of you here listening today, I had a talk on dog sledding a few weeks ago, but another personal example I can think of is that dogs have an amazing memory for trails. They can run a trail once, like for example, the Iditarod. If you have one dog who's run the Iditarod, that's a 1,000-mile race. And that dog, if it goes back there even 2-3 years later, it will remember trail points. It knows where checkpoints are it will remember that. It will remember that it's only 100 miles from the finish line, even though it only ever been there once. So their spatial memory is far more in tune, I would say, than what our brains are geared towards. And so then keeping with that mental map thing, this is most ants rely a lot on pheromones, which I'm going to come to, but this is a desert ant. It's Cataglyphus fortis, and it's really, really cool because it does something called path integration. So what that means is imagine every time you took a step, you were always doing math in your head. of, okay, this is where my front door is, and I've walked 10 steps forward, and okay, then you took 3 steps to the left and then 4 steps right. And so when they're going out searching for food, they're constantly or continually recalculating their location, so that as soon as they find it, they can then beeline straight back. Because think about it, they live in the desert, resources are really scarce, and so they'll cover, I think in this specific study, they're showing that they did 600 meters. So they covered crazy amount of distance, and then they finally found a food, whatever it might have been, maybe another insect's larva, and they beeline or antline straight back to the nest, which is really cool. But I mean, for us, right? Could you imagine being able to always know how many steps you'd taken in different directions to get back to where you started? And so yeah, now I get to switch into smells and pheromones, which is, I am biased. This is one of, I think, is the coolest. So this picture here that you're seeing, this is a green turtle, I think from Ascension Island is where this study was from. And so what they found was that females that are returning for nesting sites actually follow the smell of different islands in order to get back to them. So they'll use different navigation tactics to get to the general region, but then they'll actually come to the surface and they're able to scent out which direction they need to go in order to find a good place to build their nest, which I thought was very, very cool. And this semi-intimidating page, this is the first show of some different pheromones that have been discovered. So the bottom right that you're looking at, those are the pheromones that ants use when they're making trails. And pheromones are interesting because we've known they've existed for a couple hundred years. We knew that there was obviously something that animals were able to communicate with one another, but the molecules are so small that it took until 1959 before they were able to actually extract and identify an individual pheromone. And they won the Nobel Prize for that. And it's interesting because at the time, I think the first study was done on moths, and it took them like hundreds of moths in order to get enough, to extract enough to actually be able to analyze it. Whereas like now technology has caught up enough that out of 1 or 2 moths, you would get enough to be able to identify that. And so you can see there's the proteins, the different way they interact. And so we often think of them as smells. And I think about that if I could have, if you could have any enhanced smell, or any enhanced sense, I would want to have really great sense of smell, because there's whole conversations going on in nature around us that we're not privy to because we don't have the olfactory capacity to take that in. So that would, if I could get a scent upgrade, I think that would be very, very cool. And one thing that we don't think about smelling a lot is actually fish. So a very cool thing about salmon is that they have, they use pheromones to help navigate when they're spawning, when they're trying to return to their natal grounds. And so the way they've essentially figured this out, the way they figured out how this component works is from stray salmon. So the idea being that they either have lost contact with what they are, and so if they sort of know where they've come from, then they have this pheromone and it's not very strong. But let's say if they're, they get washed to a different side of an island, or they get moved, or they're juvenile or anything like that. So a salmon that feels like they actually amp up this pheromone, they amp up the receptors for it. So they actually, change their body so that they have a heightened sense of smell, let's say, and then they can smell other salmon. And so that's how they know to follow those streams and follow each other to get to a new spawning ground. So that will happen if, an example of this is, let's say habitat gets destroyed and they can't go there anymore. If a salmon all of a sudden doesn't have access to a stream outlet and it can't go there, it will look for a new route, but it will actually amp up its ability to smell, to find other salmon, to find a new place to lay its eggs, which is, yeah, just imagine being able to alter, you walk into a room and you're like, oh, the onions are there, you could change your sense of smell. It would be very cool. And as an aside from navigation, but just something I think is really, really cool. So these sci-fi looking creatures are lampreys, and they are a parasite. They feed off of other fish and different things. And so, but some of them are invasive species. So a lot of work that's actually being done now is to use pheromones in order to help control invasive species populations. So one thing they're doing is they're using lamprey pheromones to try and capture them, I think, in the Great Lakes, which is a really cool study, and I'm excited to follow that and see what that develops into. All right, moving to our last topic of navigation is magnetic fields. So we're going to delve into a bit of geology, not too much, right? But we know that we have the crust, and then as you move to the center, we've got the core, we have the mantle, and so with all of that iron, it's very hot and it's fluid, and so we actually have a magnet in motion, right? All of that iron in the center of our world, it creates this magnetic field around it, and that's what gives us our ability to use a compass, tell north from south, and so we're coming to realize that animals actually have the ability to pick up on this. And so one of them that we've definitely identified is the loggerhead turtle. So what you're looking at on the left with our colorful rainbow bands is different, those are the plates. So the grayed out is the continents, and then those colors is the sea floor. And so a really cool thing that we've learned about our Earth is that right now, what we call north is at the top and what we call south is at the bottom. But every 100,000 years or so, our poles actually flip. So the magnetic field, it's always kind of turning and wobbling. It's what, right? Because our geographic north, it always stays the same place, but our magnetic north sort of turns with our Earth, and depending on what's going on internally. And so it always does a little bit of turn, but every 100,000 years ago, it does a big flip. And so in the rocks, the iron in the rocks actually responds to when that magnetic field flips. And so what's really cool about the seafloor is that they can essentially map it. And you can map the seafloor based on the direction that the rock thinks is north or south. I mean, we call it north or south, but it's just relative pole changes, right? And so when it switches, it gets trapped. So think about it as, let's look at the Atlantic. So the Atlantic is a plate that's growing. So what's happening, if you can see my hands, depending on which screen you're looking on, when the Atlantic goes, the plates are separating. So new rock comes to the surface, and then it cools. And so every time it cools, it gets stuck in whatever direction the magnet force is pulling, or the magnetic field is pulling, excuse me. And so then it's like there's patterns on the seafloor. And what we've learned is that turtles, these loggerhead sea turtles, can actually pick up on the changes. So it's like, you and I, we know to turn left whenever you get to this, you're driving home. Oh, here's the stoplight. This is where I turn left, then they turn right. Instead of stoplights for them, they're actually reading, oh, this is that band. Okay, now I'm going to turn this way, and that will get me to, the Indian Ocean or whichever current they're trying to follow. Which is amazing that they can pick up on that. And so the research that was done to actually figure this out involved magnetic coils. And I'm sorry, I couldn't resist. So the coil on the left is not what they used for the study. Those are Tesla coils, and you can essentially shoot beams of electricity. I just thought it was really funny because that's how I imagined this test study. Because the way they figured all this out was they took different turtles in like big pools. They actually took birds in cages, and they put these big magnetic coils all around them. And essentially, when you put electricity through them, you can change where it thinks north is. And so imagine like a big room. And so they put all these coils up, and they put the animal in the middle, and then they would change north, and they would see what direction they would try and navigate to. And that was how they knew where they were switching, or whether they were following north, whether they were following the sides. Oh, whoops, sorry, I'm getting ahead of myself. And so another thing to keep in mind is that, I don't know if you've ever had the chance to use a proper compass. So you'll notice that you have a dial, and one side always kind of leans down. And so that's what we call inclination, because our compasses do point north, but they also point into the earth a little bit. And so some animals, they can actually change these coils, and they can find out whether an animal is in tune enough to know, okay, that's north, or whether the animal is in tune enough to know, oh, this is like what latitude they're at. So if you're a snow geese and you're flying from the full length North America, you're flying all the way up to the Arctic, you're actually, that would change for you over time because you're crossing so much distance, right? Or whales who are crossing crazy amounts of, who are going thousands and thousands of miles when doing their migration. That inclination is something they would actually want to keep track of, because that would change depending on how far they were in latitudes, right? And so they've been able to figure out which species. So they've looked at, like most study species are smaller, right? Most of the things that people have looked at are mole rats, mice, bees, ants, things like that. They're easier to do these studies on. But we're starting to identify the same cells in those animals we're starting to find in larger species. So we know that they have the same capabilities. And one of the big breakthroughs that we used in learning how they migrate was actually with rainbow trout. There was a group of German scientists, and I can't remember how long ago this was. I think this is early 2000s. So what they did was they found out that there's, it's called magnetite. Sometimes people will say biomagnetite, but basically it's just magnetized iron, let's say, for simplicity. It's got a whole cell structure, but we won't worry about that. So there's all these little cells, and they found out that rainbow trout have them actually in their nose. And so they scraped out some of the cells, and they put them in a little dish, and they found out that about 1 in 10,000 of these cells has enough magnetite in it that if you put a magnet near it, it will spin. And so they're realizing that however the message is sent to the brain, they still don't know, but when enough of these spin, enough of these interact, that's what the brain is using for them to be able to migrate, them be able to find their way. And another cell that we've discovered is one that they've termed cryochrome, which I think is a cool name. And we're discovering that it exists in a lot of different species' eyes. Even we have it, actually. So cryochrome is that, it's that magnetite, but it's in our eyes. And so people are speculating that some species might even, quote unquote, be able to see the magnetic field, not just necessarily sort of have that inherent instinct of where it is, but there's actually a visual component to them for them. So if you've got that friend who's never gets lost, maybe they've got a really, really high amount of cryochrome in their eyes. So when we think about all of these navigational techniques, right? It's important to put them into context of what the animal is using them for. So in general, we can split our nomadic species into two forms of navigation. There's homing and there's migration. So migration is moving, seasonally, different food resources, and then homing is when an animal have a home base, and then they travel out, but they generally always return to that, right? Whether they're going out for food or whatever that might be. So this was a really cool map. This was a eagle that was tracked throughout Saudi Arabia and the Middle East, going up there. I think this is for a year, the amount of ground that it covered, right? So these ones are territorial. And so when you think about these navigation techniques, some of them are employing them on the scale of thousands of kilometers. Some of them, like the desert ant that I showed you, it's navigating within a few hundred feet, but it's very, very small and meticulous. But they're all using similar strategies, and they'll often use multiple strategies at the same time. A lot of the species that are capable of tracking pheromones can also use the magnetic field, and so they never have to rely on just one. And if there's any drivers or pilots out there, this is a very specific one, right? Something they're taught is, you never want to have just one means of figuring out where you are. It's really important to have a lot of different cues to be able to rely upon. And and so we've definitely learned a lot. I think science has come a long way in understanding how these species are capable of navigating, but there's still lots of things we don't understand, and we can't really, explain why it happens. We know it happens. So like one of them is my favorite story about these kidnapped pigeons. They're not truly kidnapped, but scientists would take them and release them in different locations and see how they were able to return to their original loft. And so a lot of animal navigation does rely on imprinting. I think it's what you and I, when we think about them having this natural instinct, it's a lot to do with imprinting. And so a pigeon's first flight is very, very important. The very first time they fly is when they lock in that location of where their home is, more or less. And so pigeons that have been transported to places they've never been, a couple hundred kilometers away, will eventually return to their original loft. They will find their way back, even though they're in a place they've never been, because they're using that original imprint in combination with magnetite that's in their, I think on pigeons it's in their beaks. It's a little bit different spot there. And we've covered, I guess we've covered quite a few different species, but I wanted to highlight a few of some of the most prolific migrators, I would say, or most impressive as far as we go, and also some of your opportunities to get to interact with these amazing species. So this is a picture of a monarch butterfly honing in on some milkweed. Monarch butterflies are quite fantastic. They migrate over 4,000 kilometers. It's a multi-generational migration. So the ones that leave here are not the ones that make it to Mexico. And the trip that NatHab runs on that is the Kingdom of Monarchs, which I hope to someday get to go check out, because this is on my bucket list to be sure. But so what we've come to learn from some of the science of this is that so remember when I was talking about the pheromone portion of navigation? So monarch butterflies do use the time compensation compass, so they're capable of keeping track of where they are with the sun. But then paired with that, they actually alter their pheromones to change their life cycle so that they can make that migration. So we're going to call them migratory monarchs versus summer monarchs. So summer monarchs are the ones that are going to stay, eat, reproduce. Migratory monarchs, actually, they don't have there's a pheromone they don't have in a juvenile stage, which essentially delays, because they don't have that pheromone, so it delays their reproductive development so that they're less focused on that. And then it also lengthens their lifespan so that they can travel further. So they pair these things together so that they can make these great distances. And so one generation really is focused on just getting from A to B, and then that generation will eventually reproduce. But in the next generation, it doesn't have that pheromone. So its goal is reproduction, fatten up, quote unquote, and prep the next generation, which is crazy to see that planning for navigation across generations. Another really cool one is the migration of the gray whales. So they go, nearly the full length of North America, somewhere on close to 10,000 miles they're traveling. And you can see them at all different points along the way. Our trips, you can go to Mexico and be able to see them on the Baja Peninsula, which is pretty fantastic. And what we've learned about gray whales, remember when I was talking about cryochrome and having that in their eye? So they have those magnetite cells, those are in their retina. So these are one of the species that we sort of speculate might be able to quote unquote see magnetic fields. Although, it's like walk a mile in someone else's shoes, you'd be able to see with a whale sight, get that to be a saying. And yeah, so when we think about this, so they'll have that ability, they'll have that background magnetic field to follow, but they'll also use things, they'll use landmark cues the same way you and I do, like underwater seamounts, right? Those are really good cues of where they've traveled along the way. And one of my personal favorites, because I work in Churchill, is the polar bear. And I think they deserve some very solid props, because when you think about a polar bear, they essentially live on a conveyor belt, right? So they're living on sea ice that is always in motion. And so sometimes that conveyor belt or that escalator is moving in the direction they want to be going, and sometimes it's moving counter to where their feeding grounds are. So they have to be able to navigate. If you watch the way they move in the track, it looks very sporadic, right? But a lot of that movement is the sea ice underneath of them. And then when you think about in the summer, specific to the Hudson Bay population, so they will, when the sea ice melts, the polar bears in the south along the Hudson Bay, they retreat to land, and they all migrate to Churchill. So Churchill, I've got there's that red star on the map, kind of top left or so. So regardless of where they come to land, whether it's down by James Bay or north by Chesterfield or something like that, they will migrate to Churchill, and they know how to get around and they're keeping track of that. And they do that because that's where the sea ice comes in first. So that's their first chance to get back on come fall again, come that October, November period. And also they are really big on pheromone communication and pheromone following as well. So polar bears have, in between their toes, they actually have glands that excrete pheromones. And so when you think about this, right, they're generally quite solitary creatures, but they can leave prints in the snow, and those prints can hold their smell for 20 to 30 days, which is very impressive. And that smell then can communicate, whether that's young male, whether that's a female with cubs, a lot of that information is, and so then when you see, especially in the spring, you'll see a male follow the tracks of a female, and they really don't focus on their eyes. Their eyesight isn't that great, but their sense of smell is fantastic. And they will like follow the tracks. And we've seen this in the rover sometimes. You'll like see them and you can see the female in front of him, and he's like literally following exactly where she walked rather than just looking up and be like, oh, there she is. But that's an aside. And lastly, we're coming back to our bison. We've come full circle. So yeah, a great place to go see bison is in Yellowstone, excuse me. And when we think about our bison migrating, right? So there was a time where they were crossing far greater distances. Right now, most bison populations are either domesticated or residing in national parks in Canada or the US. So now we could argue that their need to migrate in their current living situation is not as significant, but there was a time where they were covering huge tracts of land. And and going back to those bison I saw as a kid who were just like in the fence in the northwest corner, trying to go back to northern Alberta from where they'd come. And that's largely based off of the magnetite, right? That internal compass that we talk about, of them being able to essentially feel or sense where north is, which is, it was great to sort of come full circle and answer that question, at least for myself, 10, 15 years down the line. So I hope that you all enjoyed learning that with me as much as I enjoyed sharing it with you. It's been an absolute pleasure, and I think I'll pass it to Colby to see what we've got for questions.
Okay, thanks, Kristina. I really appreciate it. It was really, really fascinating on a lot of levels. It was a great survey of navigation. We do have a number of questions. Before I start those, I'd like to remind everyone that you can submit your own questions via the questions field in your GoToWebinar control panel. So with that, let's see. How about if we just start with some general navigation questions? So some folks keyed into your idea that magnetic north is always moving, and that like even airplanes as well as people, navigating in different ways, animals have to keep up with that movement. But not everyone understood the movement. Like why is magnetic north moving? Why do we have to keep track of it?
Yeah, no. So it's a really good point. So when we think about geographic north, that's what we've all agreed this is the imaginary point on the top of our Earth, and it's based on where our Earth sits on an angle, and that's the point, and it's always there, right? It's that one spot. But magnetic north moves because it's based off of the iron core. So even though we think about it, we jump up and down, right? We've got a very solid crust, but when you go into the center of the Earth, there's a huge amount of iron and the heat and the energy, and so it's very, very slow, but it does move very, very slowly. And so it's not equally mixed. It's not as if like this is the exact same density and amount of iron here is there. And so when it slowly moves, it's like a really big magnet, and so it pulls our magnetic field with it. So it's not very fast, right? So for any of those who do orienteering or into navigation thing, right? So on your compass, whenever you want to go somewhere new, if you drive across the country or something like that, like for me, I just moved to British Columbia and I had to change the declination on my compass. So declination is when we're navigating, that's the distance that we correct for between what we call true north, so our imaginary dot, and what we call magnetic north. And so that's always changing. And actually on a sort of a fun note, our technology, so there are people who ski to the North Pole, and you have to be careful because the airplane is following a GPS point of where you are, but that GPS point is moving because the pole is actually moving a little bit up there. And so the plane has to find the skier roughly where they think they are, but then actually track them down because the GPS is moving so much. But that's just a funny aside.
Yeah, I have a lot of experience with GPSs not doing exactly what you'd expect them to do, and that comes as a surprise to a lot of outdoor recreators. Yeah. Let's see, following up on that, you were talking about how the poles every, I believe it was 100,000 years, they flip. So when's the next one? Can we put that on our calendars?
I think we're so it's give or take 100,000 years. Like sometimes they're every 150 or sometimes they're less, but I actually think we're coming close to one. And by close, I mean like if any of us are kicking around in the next 20,000 years, we might get to see it. But I think we're all safe for several generations.
Yeah, geologic time is something that's a little different than what we experience in our daily lives.
Yeah,
for sure. Okay, last specific navigation question, or I guess specific to magnetism. So we have a question about electromagnetic fields, and so in today's technological era, we are also emitting a lot of electromagnetic sort of radiation, and we're sort of messing in some regards with what you could measure and feel naturally. How does that affect animal navigation? How would that affect human navigation?
Yeah, no, that's a cool one. So that's not something I dug into for this talk, but it's sort of on the periphery. It's come up with some other things, and so as far as like when we think about things like songbirds and small birds that live in our cities, that's actually something they have to contend with, right? Think about our power lines, right? Because electricity and magnetism, we don't think about it consciously, but they are kind of linked, and so they do sort of affect that field. Here's this interesting, just small aside of things affecting. So I'm building sensors for a master's, and just the own electricity from my body actually offsets one of my sensors so that it doesn't work. Right, so there's little things that are happening, and so I imagine that animals that are moving in and out of urban environments are having to correct for that and include that in their navigation. I imagine things like gray whales that are covering much more distance, and they're not necessarily within those fields. You know, they're not having to deal with that as much. But I bet if you were to look, I'm sure someone who looks into this in the coming years, right? Of you know, are they avoiding certain areas because we have developments, because that sort of messes with their ability to find their way. I bet there's something to it.
Yeah, for sure. It seems like there's a lot of debate out there now how much that really affects us and affects wildlife rather than does it, right? Because we sort of know at this point. It's so confusing. Let's see, we have a couple questions about wildlife specifically that you were talking about, Kristina. So the warblers, other songbirds that are migrating at night, they're using the stars. What happens when it's overcast?
Yeah, I didn't talk about this because I didn't want to get too there's just so many tangents you can go down. So there's another thing, let's see if I can remember the name properly. So there's they can essentially use polarized light. So in the same way that, you know, when it's dark, it's not truly dark. There's still on the spectrum of light, like what you and I can see is light. There's a continuation of that wave above and below. And so they can actually see that refraction. And so they use that when they can't calibrate with the sun or the stars, they use that as a check-in. And so that's their backup system, is a lot of songbirds or birds specifically, I think. Some of the songbirds were the ones I was looking at. It's one of those ones where I didn't have enough time to go down the rabbit hole too much, but I'm just not, it's like, yeah, it's basically, so when you think about the horizon and sun hitting here, light sort of refracts and spreads this way, and so they can keep track of that is the simplest way to explain it.
Yeah, for sure. A lot of birds do that just in their daily life, don't they? I like that idea that it's a backup system. That's a great concept. This one's a little bit of an aside, but a couple people asked, and we hear it a lot on the Yellowstone trips, are bison and buffalo the same species?
Ah, all right. So the scientific name of North American bison, or buffalo, if you want to call them that, is bison, bison, bison. It gets all three. It's a family genus species, which is funny. So common names aside, the way that we determine whether it's a bison or a buffalo is essentially science has delineated the common term we call buffalo here because when Europeans came over, they had seen water buffalo in Asia, they had seen buffalo in Africa, and this was the closest comparison. So we kept that word, but biologically very, very different. Like, you know, they couldn't interbreed. Like, even if they somehow ended up on the same continent, there wouldn't be any crossover there, right? So if you're in North America, I grew up calling them buffalo, right? But we spent enough time, I've started calling them bison and trying to stick with that, just to make that distinction. Whereas, you know, when someone says an eagle from Africa is a different species from an eagle in North America, people would argue maybe they're not, because if they ever met, you know, there could be a potential crossover, but that's not the case here. They're very, very different.
You know, we see that a lot with animals that were sort of discovered in North America during the days of manifest destiny, isn't it? Like in fact, a lot of them are in Yellowstone. We have the bison called the buffalo, the pronghorn is called an antelope. It's not an antelope and not related.
Yeah.
Elk are actually moose if you go over into anywhere in Europe, but they had never seen elk, so they just applied that name to them. Then they figured out that they were actually moose here too. Yeah, really fascinating. Well, looks like our questions are drying up. Oh, wait, here's another one. Oh, how about monarch butterflies? You mentioned them. So some of these monarch butterflies, like they're born, you know, in more northern parts of North America, yet they know how to go back down to the Mexico mountains. How do they know if they have never been there before?
Yeah, so this is getting into that side of things that, like, even though people have spent years and years trying to figure this out, right? Some of those studies that I was showing you today were from the 50s. Like, people have been trying to figure this part out, and it's still, that part is somewhere in the genetic code, that like drive to go south, right? So we know when they decide to go because of seasonal cues, right? Temperature changes, daylight changes, that's the cue that tells them, okay, it's time for me to go. But what we don't know is what internal cue says go south, right? So right, like there's a certain amount of genetic code that no one has broke yet, and it'll be interesting to see, personally, I think in, you know, 20, 30 years as time goes by, whether that code is the same across different species as we start learning it, or whether each, you know, lots of times there's coevolution where they, you know, two species need the same thing, but this one figures out how to do it this way, and this one has figured out how to do it this way. So yeah, it'll be a exciting time in science, I think, in the next years, because we're starting to be able to get small enough to actually to look at some of these things and break those down.
Yeah, the cutting edge of science right now, especially for something like the monarchs, where, you know, what it's a number of years, isn't it, that the generations go before the new ones come. So it would have been years. It's really fascinating. Go on the monarch trip, you guys. It's exceptionally interesting. Okay, last question, quick one. Author of the Wanderlust poem that you read.
Oh, the last name is Gould, Gould. The first name starts with, I think it's a J, but I won't. But if you just do Gould and Wanderlust, you'll find the poem.
Okay, fantastic. Well, that's the last question we have time for today. Kristina, thank you so much. How about I'll throw it over to you for some closing comments.
Sure thing. Oh yeah, I hope everyone has enjoyed our trip through some of the navigation and of migratory species. I guess my closing remark would just be, you know, all these things I've talked about are species-wide traits or species-wide developments, but each animal is still an individual. They still have to learn and develop and hone their own skills and practice at things. And so I think about that, right? Like they intuitively have these tools, but each one still has to develop them, still has to get good at them. And so I think it's a good insight or crossover into, you know, nature versus nurture, and for ourselves, right? Like we we have to develop those skills, develop those behaviors, those traits of what it is you want to accomplish, right? And so, you know, we've focused on technology, and there's all these things we've used, right? But there's still things that are innately with us that you can actually, you know, push and get better at. And, you know, maybe you set your alarm clock, but you learn to wake up without it, or things like that, right? It's good to explore those things, both learn about them in nature, but then also, you know, think about yourself as well. So everyone, take care. It's been an absolute pleasure. And yeah, check back in for another talk in a little while. I think I'm back in a few weeks or a month.
Oh, well, that's great, Kristina. We look forward to it. Thank you very much for everything you put into today. I'll pass on that. We've received a lot of comments thanking you for a very interesting and informative presentation. So thanks for all the work you put into it. It was really enjoyable. I'd like to also thank everyone who joins in today. Join us again tomorrow, of course, for our next Daily Dose of Nature. You can check out this week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and we'll have the replay available on our website soon. And with that, I will conclude today's webinar. Thank you, everybody.
Take care, everyone.